Good afternoon and welcome to Pre-Calculus. We are starting Chapter 1. Chapter 1 is called Functions from a Calculus Perspective. Today our lesson 1, is all about functions. So let's get started. The first thing I want you to go over again is to review the idea of sets. Now I know just last week we talked about sets and how in reality all of math is based on sets. Well, this is even more true when we get into our problems here. So these are the real numbers. The real numbers you already have dealt with multiple times. And inside these real numbers, we have rational numbers, which are Q. We use this scripted Q as rational numbers, and a scripted I as irrational numbers. Now, irrational numbers that you already know are things like square root 2 and square root 3, pi, e, all of these things that are decimals, but they never repeat. Those are the irrationals. Now, of the rationals, those can be written as a fraction of some form. In the rationals, you have all the integers, because I've already taught you that when you have these integers, like here, you can write 8 over 1. That is an integer, and that's part of the reason why it's in a rational number. And then you have the whole numbers. Whole numbers are numbers that are non-negative. So you have 0, 1, 2, 3, all the integers that are not negative. And the natural numbers are the numbers you learned from a child when you started with 1. We don't normally count 0. It seems kind of odd when you start counting with 0. We always start counting with 1. So natural numbers are the ones that you just naturally start counting with. Whole numbers are the ones that are positive that we use. Integers include the negative ones. All of these are rationals that include fractions and decimals. Irrationals are decimals that will not end. Now, to help put this into some perspective for you, all of these are in a bigger set of the complex numbers. And we usually use a little scripted C here for the complex numbers. It looks better if I try that again. Sometimes we just do this. That's the complex numbers. And every real number is also in the complex numbers. And then the complex numbers would be in a larger set of just items, because you've got to realize these are all numbers. And then you've got other sets that you can use, like sets of mattresses or people or all these other things. And so these are just dealing with sets of numbers. All right. So as we go through this, let's see if I can advance my slide here. As we go through this, we're going to have to build notation, because we need to know what set of numbers we're talking about. So in this problem, we're talking about a set of problems or a set of numbers where it's just x. We're not talking about 2x. We're not talking about anything. And x is always going to be between -3 and 16. And x is an integer. So then you can actually know from this information that this is the set of -3, -2, -1, 0, and it keeps going all the way up to 15 and 16. And then we can close the set. But rather than writing this long thing, we're simply saying the numbers such that this number is between -3 and 16, and it's an integer. This tells us that this number is what we're dealing with. The vertical line is the word such that. That's how it's read. And then this is one property of x, and this is the set that x is in. Sometimes you'll have multiple properties for x. Sometimes right here could be an equation to find, and so it could be y such that y equals 2x and x is something else. You can see things like that all the time. All right, so let's try and use some set builder notation to work these problems. So here, we are working our first problem here, and we have the set of x such that x, and then I'm looking at these, and natural numbers start at 1, go to 2, 3, 4, 5, such that x is an element, don't forget those little symbols that we learned before, of the natural numbers. And then I close my notation. So rather than having to list them all, this lists them all already. How about this one? X can be anything less than -3. So I'm going to deal with my set here, x, such that. Now I know x needs to be less than -3. Now my question is, what kind of numbers can I have? X can be integers, but x could be fractions. It could be irrational. I mean, I could have -√2 or -pi. So this, I would do x is an element of the real numbers. And then lastly, all the multiples of pi. Okay, all the multiples of pi. So again, I'm going to say, using set builder notation, my number such that. Now, I'm going to have to come up with x. So x has to be a multiple of pi. So let me get my x here. And this has to be equal to pi. And then I'm going to multiply by a number, because I need to multiply and find every possibility of this. Now, I need to decide what is n. Okay, well, n can be 1, 2, 3, 4, 5, but n could also be -1, -2, -3, -4, and n could be 0. So n has to be an integer. And then we do the closed notation. And this will give me every single multiple of x, and it will list them as numbers. All right, think through that a little bit. It may be complicated at first, but you can think through it and get it. All right, here we go. Next one, we need to know interval notation. Now, I'm sure all your life you've been taught that you must, if you have a closed bracket or an open bracket, you must have a closed bracket. Or if you have an open parenthesis, it must have a closed parenthesis. Well, math is choosing to break a rule that you thought you knew was true. The bracket and the parenthesis can go together. Here's the rule. If it can equal to something, then you have the bracket. Okay? So if your function has something that looks like this, a less than or equal to, or a greater than or equal to, this implies that you will have to use a bracket. Okay? It's not necessarily on both sides. It could be one side or another, because you see here, I have it only on one side and not on the other. If I just have a strictly less than or a strictly greater than, I need to use parentheses. Okay? This is part of how I will learn to list things. Now, one thing I do want to make a comment on, and this helped me remember this kind of thing, is if you have a number line and you're trying to get to this point, and I'll call it A, trying to get to this point but I can't equal it, you get this little curve that gets as close as you can and it doesn't touch, like a parenthesis. But if I can be at A, then I just draw the little edges off of it and I go straight from A, like a bracket. So if you can think of it as, if I can be on A, I get a bracket, and if I can't quite be on A, but I can get very close, a parenthesis, you can get this part right. Also, if you don't have a bottom or a top, of your, so all of these inequalities are all bounded. All of these have an upper and a lower bound. I can't get past certain numbers. But here, anything above A works. So if anything above A works, then I can go all the way up to infinity. And you can never reach infinity, which is why infinity will always have a parenthesis. If you said, okay, I am finally at infinity, this is where it belongs, I could come and say no, because I can have that number and then one more and be farther than you. So you can never really reach infinity on a number line. It just keeps going as you never get there. And so you can't hit infinity. You can't equal infinity. So that's why we have a parenthesis. All right, ready to try some of these examples? Example, let's try this first example. Okay, interval notation. I know that y is going to be between these two numbers. So I'm going to start by listing those two numbers, -4 and -1. Okay, y has to be between those. Now, if y is between those, but it can equal to, notice here, equal to 4, then I'm going to have a bracket on 4. But it does not equal to 1, so I need a parenthesis on -1. How about this one? I can equal -3. So I've got -3, and I know I can equal it. But anything larger, all the way up to infinity will work to solve this inequality. Also, something, just a word of warning in case you ever have an issue with this. You must list the smaller number and then the bigger number. If it's in a reverse order, you will get the answer wrong. It's always from the left to the right, the smallest to the biggest. All right, how about this one over here? Well, looking at this problem here, I know this one and I know this one, but I don't know if they overlap. This one says that I have to be less than -2 or bigger than 9. So there's a gap in the center that I can't have. So I'm going to start by writing this inequality because it's smaller than that one. So I can go from -infinity, and I can't reach -infinity, to -2, and I'm not allowed to be at -2. And I'm not allowed to be at 9, and then I can go all the way to infinity. Well, my answer is going to be both of these. So I need a way to connect them. In interval notation and in sets and everything, we use the same symbol as sets. We say union. This big U, which is union of two sets. And it's read as union. It means this and this, the two sets together. All right, a function. Now, I know we've gone over functions many times before, and you've been working with them in Algebra 1 and Algebra 2 and geometry and everything. But now we need to think of functions from a set perspective. So a function will take values from one set and match them with values from another set. Now, these two sets can be the same, and in many of the things that you have dealt with, it's real numbers onto real numbers. And that is why it seems like a function is simply changing a number. But it's actually one set to another. For example, if I had a set of all the pictures at the school, and I matched that with the set of all the names of the people at the school, it would be a function because for every person, every picture of a person, there would be a name. Now, the same is not necessarily true if you go by first names to pictures. Because if you have two people with the same first name, then their name would match onto two different pictures. So one big thing about functions that you need to know here is these values can only have one option. Now, if for some reason, suppose number 1 also mapped to 7. If it mapped to 6 and to 7, this would be not a function. Okay? In order to understand functions, you must realize that a function is only possible if it maps to one number and only one number. In this example with 2 and 3, you can see 2 maps to 8 and 3 maps to 8. That's perfectly fine as long as 2 doesn't also map to 7. For just the one value of 2, I have only one value of 8 that I will ever receive. But if I was matching first names to pictures, and I picked the right first name, I may get 2 different pictures of 2 different people. And then it's not a function anymore. Also, if we deal with domains, okay? So set A is the domain, okay? The domain, this is how we often will write it. D equals, and then we have to do these braces because we're listing numbers. Remember that the parentheses and the brackets mean that every single real number between those values are okay. Here, we don't have 1.5. There's no 1.5 here, so we have to list the values with braces. And set B contains the range. Okay, it contains, meaning that not all of set B is the range. That's why 7 has nothing. We also write the range in this form. All right, are you ready to give this a shot? Let's try it with an example. Well, before we can do an example, we have to explain about functions. We express functions in different ways. We can express a function verbally. So I can tell you the output value is 2 times the input value plus 3. And that means that's 2x plus 3 of whatever x is when you plugged it in. We can use new numbers. And this is where we would list the points. So if I gave you a list of 4 points, that can be a function. Doesn't always mean it is a function, but it could be a function. I could plot the points on a graph. And using the graph, you could see the function because it maps one to another. We could also express a function algebraically, and this is the way you have seen it the most. Things like y equals 2x or f of x is x squared. Those are things that you are used to seeing. But I want to show you when we come to a graph, the vertical line test. Sorry, it shouldn't be vertically, it should be vertical line test. Okay, the vertical line test. If you have a graph of a function, okay, that curved out more than what I wanted it to, like this. Okay, the vertical line test states that if you draw straight lines up and down through here, you can only cross the function once. If that is true everywhere, then you have a function. Okay, if you have a function and it does this, comes backwards just a little bit. Okay, here it's all crossing only once, but in one place, or here multiple places, I can draw and cross the function at 3 locations. This is no longer a function because it failed the vertical line test. All right, so now I believe we are ready to look at functions. Here we go on an example. Okay, we're dealing with these examples and we need to be able to determine if it is a function. Okay, our goal is to find out, is this a function? Okay, that's all we're doing. Function. So I'm going to start with this one. The area code for you guys there in Hoover is 205. Okay, and so the input value is the area code, And the output value is a phone number. So the question is, if I put in 205, will I only get one phone number? No, because many people have the area code 205. Now, if it was the other way and I gave a phone number and it gave me what the area code was, that would be a function because there's only one phone number, even though multiple phone numbers will match to the same area code. But the way that it is written is not a function. So this one is not a function. All right, next we're going to look at this one, okay? I need to be sure that for every x value, so I'm looking at x, I only get one y. I only can have one unique y for each x. So -6, 7, fine. 2 to 3, fine. 5 to 8, that's fine. 5 to 9, this is no longer fine. 5 is now mapping to 8 and mapping to 9. Sorry, that should be a 9. Because it is mapping to both places, it makes the issue, I'm going to draw my 9 in red, because that's where the problem came. I can't have 5 mapping to 2 places. It does not work because when I plug 5 into the function, I won't know what my answer would be. So this is not a function. All right, how about C? To do C, I need to see if it passes the vertical line test. Okay, so as I'm going up like this, oops, I got crooked. That passed, passed. Okay, there's nowhere on this graph, it's always moving some over. You can see it better in the print, how it's always moving over a little bit. So it will pass the vertical line test. This is a function. And then finally, this one. Well, to know if this is a function, I need to solve it for one of the variables and see if as I solve it, I only can get one answer. So I'm going to start by moving 6 over. So I get 3y equals -6x plus 18. I need to divide everything by 3, so I get y equals -2x plus 6. This is a function because I am only getting one answer. Now, if, for example, I had a y squared equals 2x, then there's more than one answer because I'd have to end up with the square root and I get y equals the square root and it's plus or minus. Remember, when you add the root, you've got 2 roots. This is why it was important in the last chapter that I taught you when you needed the plus and minus, when you needed to use the absolute value. There are 2 possibilities because this is even. So, as it's written, okay, this down here was an aside. As it is written, this is a function. All right, let's move to the next example. We need to be able to find the values of f of x. Now, you guys are probably used to doing this. You've done this multiple times before. So let's just plug it in. To find f of 12, I'm going to go through this one pretty fast. I'm going to plug 12 in here and I would get 24 plus 3. This is just 2 times 12 over 12 times 12 is 144 minus 24 plus 1. Okay, that's going to be 27 on top, and on the bottom, this would be 121. And there's my answer. Here, I'm simply plugging a 6x in. So f of 6x. Now, when I plug it into this location, I'm going to have 2 times 6x. That's going to give me 12x. Okay? Plus 3. All over x squared. I'm going to square both of these things, and so I'm going to get 36x squared. Minus, and then 2 times x again, so minus 12x plus 1. And that is my answer. All right. Plugging something like this in will take a little bit more time and effort. Okay? So I'm going to write this one out a little bit more. F of negative 3a plus 8 will be 2 times negative 3a plus 8 plus 3 all over negative 3a plus 8, and I'm going to have to square that, which means I need to FOIL, minus 2 times negative 3a plus 8 plus 1. All right, so let's start working through this problem just a little bit. I'm going to move this over. This is part of the reason why I left this space here. Okay? I'm going to come and I'm going to work this over here. Okay? So I'm going to get this to be equal to 2 times 3a is negative 6a plus 16 plus 3 all over. Now I need to FOIL this. So I'm going to take a moment here in this little space right here where I'm not working right now and FOIL this thing. So I'm going to get negative 3, well, let's just start by FOILing. I should take a second here to show you how to FOIL it, but I need to have it in a different color. All right, I'm going to put this in blue, and we're doing negative 3a plus 8, and I'm squaring it. Okay, so negative 3a times negative 3a is 9a squared. Negative 3a plus 8, or times 8, is going to give me negative 24a. Negative 24a, negative 24a, because I'm going to do it twice, once for 3 times 8 and then once for the, and so for the outer and the inner it's going to look the same, plus 64. So then on the bottom over here, I am going to be able to put this part in the denominator because this is that. Okay, so let me change my pen color back. And we now have 9a squared minus 48a plus 64. And then I have this negative 2 times negative 3a, which will be plus 6a. And then negative 2 times 8 is minus 16 plus 1. Finally, what I need to do is simplify this. I'm still going to have the top, the negative 6a is going to stay the same, but I'm going to have plus 19 all over 9a squared, and then I'm going to put my negative 48a plus 6a together, and I'm going to get negative 42a, and then I'm going to have 64 minus 16, which is 48, plus 1, which is 49. plus 49. And this is my answer. Now I'm not sure, I may have left space to do this on the next slide, in which case we'll skip that slide. Yeah, see, I left space so that we could have done it here. Sorry about that, I crowded the last slide. All right, we need to be able to find a domain as well. So with polynomials, anytime you see a polynomial, it will always be from infinity to negative infinity. It's defined everywhere. The domain is everything. However, when you have a rational equation like this, the denominator, this part, can never equal 0. When it does, then f of x is undefined, and we don't want it to be undefined. So to find the domain, I know it's going to be everything except these values that make this 0. So I need to find those values. X squared plus 7x plus 12 equals 0. When is this true? Because that's not in the domain. I need to see, can I factor this? And we are lucky we can factor. And we get x, and the factors of 12 are 3 and 4, and you can add them to make 7, so I'm going to have a plus 3 plus 4, and this equals 0. So x plus 3 equals 0, or x plus 4 equals 0, and then x equals 3, x equals 4. These are the values that I am not, negative 3 and negative 4. These are the values I am not allowed to have. So I can write this in a couple different ways. I am going to show you how to write this in both builder notation and in interval notation. So in interval notation, so starting with interval, because I believe Alex will want interval. Interval notation, we start at negative infinity, and we come all the way up to negative 4. And I'm going to union that with the negative 4 to negative 3. Now watch your negatives. Remember, negative 4 is smaller than negative 3. And then that is going to be from negative 3 all the way to positive infinity. Okay? So that is the interval notation. Yes, in this method, it got very long. So what about set builder? Set builder notation. So I need x such that x does not equal negative 4, x does not equal negative 3, and we can write it saying x has to be a real number. And that's the set builder notation. All right, let's try this again with another domain. So we need to find the domain of this. Now, as we learned in the last chapter, this inside can't be negative and still be real. So this has to be greater than or equal to 0. So a squared minus 4 has to be greater than or equal to 0. So I need to find what value makes this 0 and then what makes it greater. Now, this also means, so let's solve this inequality. A squared is got to be greater than or equal to 4. I'm going to square root both. I'm going to get a has to be greater than or equal to 2, or remember there's a plus or minus here, and the plus or minus is going to shift my thing. A has to be less than or equal to negative 2. Now, to help you think through this, because of the plus and minus and the squares, we need to check that 0 will happen with both of these. So I want you to try, this one's kind of intuitive. If you plug a 2 in there, you get 0. Negative 2 times negative 2 will still be positive 4, and then that will be minus 4, that will still be 0. Now, why would I say less than? Because this is where a lot of people get hung up. Okay? If a is negative 3, so let's try a equals negative 3. Then I get the square root of negative 3 squared minus 4. That's the square root of 9 minus 4. That is the square root of 5. And the square root of 5 is defined. So we have both of these possibilities. Don't forget, when you add the square root, you have to have the plus or minus. And whenever you have multiply by a negative, you switch the sign. So this negative switches the symbol. All right, so interval notation. I am going to have 3 intervals again. And I'm going to go from negative infinity. Can't get there. Can't be, oops. Can't close my parenthesis until I finish writing what's inside. So I need my eraser. And I'll keep working here. Negative 2. And I need to combine that with the interval from negative 2 to 2. Well, actually, I can't be from negative 2 to 2. So I just made another mistake there. In this, I have to be either smaller than negative 2 or larger than positive 2. So even though there's an interval there, I don't have to put it. I need to start at 2 and then go to infinity. Okay, so from negative 2, negative infinity to negative 2, and then 2 to infinity. This is where it's defined. How about set builder? Okay, what if I do set builder notation? Here, I need the value a such that a is greater than or equal to 2, or a is less than or equal to negative 2, comma, a is a real number. And there's my set builder notation. I hope this is kind of making sense. We're going to do this one more time, but it's going to be a little bit more complicated. All right, here we have both the denominator that can't be 0 and the square root that can't be negative. So I know this inside, I know that 2x plus 6 needs to be greater than or equal to 0. Well, what happens when it's equal to 0? If it equals 0, then the denominator turns to 0, and I have another problem. So I can't be equal to 0. So I'm going to solve this as 2x plus 6 has to be strictly greater than 0. Because if it's equal to, my denominator will not work. So I can't equal 0. As I am looking at this problem, I'm going to start by solving it just like I would a linear equation. 2x is greater than, and I subtract 6 from each side. Divide by 2, x is greater than negative 3. So this is the only information I need. As long as x is greater than negative 3, this thing is defined. And because there is no square, I'm not square rooting, and so I don't need to deal with like what I did last time with 2 intervals. All right, so the interval notation. I need my smallest number, but I can't equal it, is negative 3. My largest number is infinity. And set builder. I have x. Let's not make it a. I was going for a from the last problem. Let's make it x. X such that x is greater than negative 3 and x, oops, I've got to make x as a real number. Not used to using this pen and stuff here and writing on the computer yet. Sorry guys, takes a little bit longer. All right, so x is an element of the real numbers. All right, let's try the next kind of problem. Looking at this problem, we have a step function, or it is also called a piecewise defined function. It's not really a step function because they're not straight lines, but it's a piecewise. That means each piece is defined differently. So if you look at this, as long as t is in this range, I'm going to use this equation. Okay? As soon as t moves to this range, I use a different equation. So I'm going to solve the three of these right here. V of 5. Okay? Well, that means I'm using this first equation. So then I say V of 5 equals 4 times 5, which equals 20. V of 15, okay? 15 is this end bracket, but I've got to find which one equals 15. So if you look here, this equals 15, where this one does not equal 15. So I need to use this top formula and not the bottom formula. So V of 15 equals 4 times 15, which is 60. In this case, it wouldn't have mattered, but you do need to watch that. It's one of the things that people like to throw at students, where they put something like this and you plug it into the wrong one and you get the wrong answer. All right, V of 245. I'm going to look here, and 245 is in this last range, and so I need to consider here V of 245 equals -6 times 245 plus 1500. So -6 of 245, I'm going to do that on my calculator real quick so that I can keep up and not make this too long. -6 times 245 is -14. -1470 plus 1500. 1470 plus 1500 is 30. These are my answers. Okay? That's how a piecewise function works. Now, I added this problem because I really wanted you guys to see how to do this. In calculus, this is a very important difference quotient. They call it a difference quotient because there's a difference on top and it's a fraction, a quotient. But this is the basis of a lot of calculus. And we actually play with this kind of function a lot. And I can't emphasize how important it is to understand how this works. So this will be on your homework, and it will be here in the video, and it's important to understand. I am doing a quadratic formula. This may take longer, so I do have the next slide available as I work through this. But high emphasis, this is an important problem. So I'm going to start by finding f of a. Okay, f of a equals, I'm just putting an a in for every x. A squared minus 6a plus 8. Next, I need f of a plus h equals, okay, now this means I need a plus h squared minus 6a plus h plus 8. Don't forget to add these in. A plus h is the x value. So now I need to FOIL this. When you FOIL it, you will get a squared plus 2ah plus h squared minus, now I'm going to distribute my 6, so I get 6a minus 6h plus 8. Okay, so that is my other value. Here's one, and then here's the other. I have now found f of a and f of a plus h. Now I'm going to change my pen color, and we are going to work through the other problem, this difference quotient. So let's start up over here on the top, and I'm going to start by plugging in this value. So we just found this, a squared plus 2ah plus h squared minus 6a minus 6h plus 8. And then I need to subtract a squared minus 6a plus 8. And all of this will be divided by h. So as I look at this, this negative sign is going to go to each one of these. So I'm going to rewrite this with a negative sign. A squared plus 2ah plus h squared minus 6a minus 6h plus 8. Distribute the negative, minus a squared plus 6a minus 8. All divided by h. It looks like a mess, doesn't it? Well, this 8 and this 8 will cancel, and they just go away. This a squared and this a squared will cancel, and they go away. This 6a and this 6a cancel, and so they just go away. So I am left with 2ah plus h squared minus 6h all over h. Well, now I can factor the h out and cancel it. So let me factor it out. H times 2a plus h minus 6 all over h. Those cancel out, and I'm left with 2a plus h minus 6. That is my answer. Okay? Your answer will simplify to something like this. All right. I believe I had enough space, so I don't think I need the next slide. And so this slide is blank. That is the end of the lesson today. Work through the problems. Let me know if you have any difficulty with them. And I will see you tomorrow.